Hey, Dad, what are you doing?
Savannah, I'm reading about this incredible young man who worked as a clerk in the Swiss patent office. He came up with some phenomenal ideas about relativity, time, and other things. I sure hope his work gets credited somehow and people learn about this. Did you need something?
Yeah, I was working with my complex cobalt ions, and I was wondering if you could control the direction of the reaction.
You know, this reminds me of another young man that once did some work in science. His name was Henry Chatelier. Let me explain it to you. Le Chatelier's principle simply says that if you change one of the factors that determine equilibrium, well, then the reaction will adjust itself to offset that change. Let me explain using these styrofoam balls and some random things I found in the classroom. Imagine this represents a reversible chemical reaction, and right now, at this very moment, it's at equilibrium. Now, if you were to say, add some additional reactants, the reaction would then move to offset this change by consuming some of them and creating some more products to reach equilibrium once again. So, by adding reactants, it would drive the reaction to the right, creating more products. And what's really cool about this is the same happens in the reverse. If I was to add products, it would drive the reaction to the left and create more reactants.
Wow, that's incredible! But I thought you could just add heat to the reaction.
Savannah, that's a common misconception. People always think adding heat will drive the reaction forward. It will make the reaction faster. However, adding heat to a reaction and applying Le Chatelier's principle is a little more complex than that. Let me explain. I happen to have had these laying around my classroom. If this was an exothermic reaction, we could think of it as such, by heat being released as a product. Now imagine you're adding heat. You're adding a product. This will drive it back to the left, creating yet more reactants. Ooh, there's more.
There's more?
Yes, imagine that the heat was one of the reactants. This is the case in an endothermic reaction. If you add heat to this side now, it'll drive it to the right. So adding heat does affect equilibrium. However, it depends on what kind of reaction it is, whether it's endothermic or exothermic. Here's another thing that I don't think you've thought about. Luckily, I brought in this beautiful charge cord so I can see if I can explain. Imagine I contain this entire reaction inside of this space right here, right? Well, what would happen if I closed it even further, creating greater pressure in the container?
Jeepers! What's gonna happen?
Well, the reaction is going to have to do what it can to offset this increased pressure. And the only way to do it is to reduce the number of molecules in there. And it'll actually go to the side of the equation with the fewer molecules. And being the coefficient was a 2 on this side, I would actually find the reaction would convert some of these to reactants to offset that change.
Oh, wow, that's incredible!
I know. Now, Savannah, just last night I was thinking about these things, and so I wrote a summary of what Le Chatelier's principle would do to reaction. Now, all of these things are very important for you to understand. Something very important also is the effect on the equilibrium constant itself. Notice it doesn't really change most often when you add or remove products or you change the volume. However, when you adjust the heat, it does affect the equilibrium constant. And that's important to remember.
I will remember that for sure, Dad.
Okay. Why don't you go back and play with your cobalt complex ions now?
Okay, thanks, Dad.